Dear students, welcome to my YouTube channel PCM Academy. We are in a lecture series on quantum mechanics. Basically, in the name of quantum mechanics, we are actually discussing whole syllabus of modern physics. So, from the very basic point, from the very basic aspects of modern physics, something like particle aspects of wave and the wave aspects of matter, I have started from the very basic principles of quantum mechanics. Okay. So we are actually in Compton effect, and that is today we'll discuss about Compton effect. But previous class, if you see the playlist, you can see that in previous class we have discussed about something like photoelectric effect. Okay, so photoelectric effect was the first experiment which proved that the wave have particle nature. So radiation have particle nature, that is particle aspects of radiation. So we have discussed all the things about photoelectric effects, and now we are going to discuss about the second phenomena, that is Compton effect, that also raise the voice in favor of that the radiation have particle aspects also. So we have divided these chapters in two ways. One is the particle aspects of wave, and another is the wave aspects of particle. Okay, so we'll discuss later on the wave aspects of particle also, but now we are discussing the particle aspects of radiation actually. Okay, so photoelectric effect is one of the phenomena which actually claim that the wave has the particle, radiation has the particle behavior. Similarly, Compton effect also uh, can be very well explained by using the particle theory of radiation, and it cannot explain by the wave theory of radiation. So first let us tell you what actually Compton says, okay, or what actually Compton observed in this experiment. So basically, what is the experiment? So suppose here is an electron. So let us take a color first. Okay, so suppose here is an electron which is taken initially as a rest. Okay, so this is an electron, and wave of X-ray photon is incident on this electron. Okay, so wave is incident on this electron. Okay, of wavelength lambda. Now, if you observe the scattered photon in different angle, suppose this is one of the scattered photon. Like this. So if you observe the scattered photon in various direction, so Compton did this actually. He observed this scattered photon in various direction, but he observed for two directions. So there is a different that in two directions there is intensity peak of this scattered radiation, and that peaks are at lambda and lambda dash. So one is at, suppose one is at lambda and another is at lambda dash. So he observed one scattered radiation which of wavelength lambda, which is same with the incident radiation, but another one I have the wavelength lambda dash, which is different from lambda, and it is seen that this lambda dash is greater than this lambda. So this wavelength shift of for another peak, that is for the wavelength shift, that is lambda dash minus lambda, which is delta lambda. This cannot be explained. This cannot be explained with the help of electromagnetic theory existed at that time. Okay, so according to electromagnetic theory, at any direction, if you observed at any direction, the scattered photons would have same wavelength or have same frequency as the incident radiation. So classical electromagnetic theory says this. But here what we can see the different wavelength for one particular intensity peak. You can see the different wavelength. Okay, so that result is observed actually according to the classical electromagnetic theory, because according to classical electromagnetic theory, if the frequency of this incident photon, suppose if the frequency of this incident photon is new, then the electric field of this electromagnetic radiation will oscillate this electron, will fall on this electron. So the electron will be oscillate according to the frequency of this, with the same frequency of this incident radiation, and it will emit electromagnetic radiation of same frequency. So as the frequency as well as the wavelength should be same for this scattered radiation also, according to classical electromagnetic theory. But Compton observed that to different intensity peak or to different lambda, one is as expected, that is lambda, which is same as the incident radiation, but another is unexpected, which is lambda dash, that cannot be explained by using the classical electromagnetic theory. In that case, Compton explains this phenomena by using the particle aspects of radiation, and he assumed that this electromagnetic wave or this radiation is a stream of photon particle having energy h nu. So when the particle is colliding with this electron, so he actually assumed that this is a collision process of photon and electron. So when photon collide with this electron, it will lose some energy and its energy will be decreased. So this will be, the energy will be h nu dash, so nu dash will be less than nu, so that lambda dash is greater than lambda. Okay, so he can explain this wavelength shift delta lambda. So let us mathematically measure this shifted wavelength. So how we can measure this shifted wavelength delta lambda, that is lambda dash minus lambda for this case. So for that we will use this particle aspects, and we assume that the radiation of h nu frequency is incident on this electron, and h nu dash energy, the photon of h nu dash energy will be scattered at some angle phi. Okay, and the electron will also be recoil with some angle theta. Okay, so let us calculate this delta lambda. Okay, so let me redraw this diagram again. So suppose there is electron, so let us take this electron initially at rest, and also we assume that this electron is free electron. I will explain later on that why we use this electron as free electron. Okay, so this will be the incident wavelength. Suppose the incident wavelength of photon is lambda, suppose, and this is nothing but the scattered wavelength. This is scattered photon, is lambda dash, and the scattered photon is scattered at an angle phi with this incident direction, and along this direction the electron will be recoiled. The recoil electron will be along this direction, so the angle is theta, so it will recoil at an angle theta with the horizontal. Okay, so now let us take momentum conservation and the energy conservation, as we know from the classical collision theory. So suppose the rest mass of electron, we can assume that m0, and this electron is taken as free actually, because the kinetic energy of this recoil electron is so high with respect to the binding energy of this electron within the atom. So the electron has very less binding energy with respect to this electron, the kinetic energy of this electron, so that we can use that, we can assume that this electron is free. Okay, so but if this electron is not free, then the case will be different. We will discuss later. Okay, we will discuss later. If this electron is not free, its binding energy is very high, then actually the wavelength will not be visible, not be measurable, because in that case we have to use the mass of atom instead of the mass of electron. So we'll tell you later on, after giving the mathematical expression. You can easily understand why we cannot measure if the electron is not free, why you cannot measure the Compton wavelength Compton shift. Okay, that is delta lambda. So first let me derive the expression of this delta lambda in terms of scattering angle phi and in terms of the mass of the electron 0. Okay, so if you take the momentum conservation along x-axis, so let us first take the momentum conservation along x-axis. Momentum conservation along x-axis. Along x-axis. Okay, so the initial momentum along x-axis, what is the initial momentum? H by lambda. Okay, and the momentum of the after scattering, the momentum of this scattered wavelength lambda dash, so along x-axis it will be h upon lambda dash into cos phi, and electron, if the momentum of electron is p, let us take, then in this direction it will be p cos theta. So p cos theta, so initially it is h by lambda and later it is h by lambda dash cos phi plus p cos theta. So we can write over here this is h upon lambda equal to p cos theta plus h upon lambda dash into cos phi. Okay, and if you take y-axis, so what will be the momentum along y-axis? Momentum conservation y-axis. So initial momentum along y-axis is 0 before collision, and after collision the momentum of electron along this direction and the momentum of photon, scattered photon, along this direction. So that will be h upon lambda dash sin phi. Okay, and this is p sin theta. So you can write this p sin theta as equal to h by lambda dash sin phi. Okay, sin phi. Now if you want, you can find out p cos theta from here. So we have p cos theta also equal to h by lambda minus h by lambda dash cos phi. Okay, so if you take this or equation 1 and this is equation 2, and we will get another equation also according to energy conservation. So if you use, so according to energy conservation, what we will get? We have the initial energy in example AC by lambda, energy of actually photon. Okay, AC by lambda, energy of initiated photon before collision, and before collision we have to take the rest mass energy of electron, and that is nothing but m naught c square. And after collision the energy of scattered photon is AC upon lambda dash, and the energy of recoil electron, this will be relativistic energy, and that will be root over m0 square c to the power 4 plus p square c square. So you can take this as equation 3. Now using this equation 1, 2 and 3, we will find delta lambda, that is lambda dash minus lambda. Okay, so let us solve this 3 equation. So first what you have to do, just square and add this to equation 1 and 2. Okay, so that will be p square cos square theta and p square sin square theta. So if you add this square and add, squaring and adding 2 plus 1, what we will get? We will get p square sin square theta plus p square cos square theta plus p square cos square theta equal to, you will get h by lambda dash sin phi, that means h square, upon lambda dash square into, I think it is sin square phi, yes, sin square phi plus what we have in the right hand side. So here is h upon lambda minus h upon lambda dash cos phi, h upon lambda minus h upon lambda dash cos phi, whole square. Okay, so now if we take common p square, the sin square theta plus cos square theta will be 1, so it will be simply p square equal to h square upon lambda dash square into sin square phi plus, this is a minus b whole square, you can take it, so it will be a square minus 2a plus b square, so it will be h square upon lambda square minus 2h square lambda dash cos phi plus h square lambda dash square actually cos square phi. Now you can see again, here is sin square phi, here is cos square phi, so if we take common h square upon lambda square into sin square plus cos square, that is 1, this is lambda dash square actually, plus h square plus lambda square minus 2h square lambda dash cos phi. So this is your p square. Now if you see the energy equation, here we need p square c square, so let us multiply this equation with c square. So you will get just here p square c square equal to h square c square upon lambda dash square plus h square c square upon lambda square minus 2h square c square upon lambda dash into cos phi. So let us take this equation 4. Now let us resolve this equation also, and let us find out p square from here, p square c square from here. Okay, so we have the equation. Let me calculate here also. Okay, so if you take here m0 square c to the power 4 plus p square c square, and if you square, then you will get hc upon lambda. Let us take this ac by lambda dash left side, so it will be ac by lambda dash whole square, this plus m0 c square and square of this term. Okay, because here is root, so if you remove this root, you have to square both sides. Okay, now if you square this is again a plus b whole square. So what we will get? So we will get, let me write this equation here. So what we have m0 square c to the power 4 plus p square c square is equal to hc upon lambda minus hc upon lambda dash whole square plus m0 c square. Let me check again. hc upon lambda minus hc upon lambda dash 0 c square, sorry, there is no square, and this. Okay, now you have to solve this. Okay, so it is m0 square c to the power 4 plus p square c square equal to, this is again a plus b whole square, so a square plus 2a plus b square we can use. So it will be hc upon lambda minus hc upon lambda dash whole square plus 2 h square c square upon lambda dash into m0 c square plus m0 square c to the power 4. Now this m0 square c to the power 4 and m0 square c to the power 4 will be cancelled out. So we will get p square c square here only. And what is p square c square actually? P square c square means this. So let us put this h square c square upon lambda dash square minus h square c square upon lambda square plus, okay, plus and minus 2h square c square lambda dash 2h square c square lambda dash cos phi equal to, now let us take this again a minus b whole square, so it will be again a square plus b square, so h square c square upon lambda square plus h square c square upon lambda dash square minus 2h square c square upon lambda dash 2ab, okay, square plus b square minus 2ab, okay, plus 2h square c square upon lambda dash into m0 c square. Now again this term and this term will be cancelled out, this term and this term will be cancelled out. So now if you take this left side, so it will be plus, so if you take common 2h square c square upon lambda dash into 1 minus cos phi, so here is cos phi, so it will be 1 minus cos phi, and that will be equal to this. So this is 2h square c square upon lambda dash, I think one term is missing, a square plus b square plus 2ab, yes, this term is not correct actually, this term is not correct. Okay, because this is 2ab and a is ac upon lambda minus ac upon lambda dash. Okay, so we cannot write this term, we can't write. Okay, so this term is wrong. This term is wrong. This term is wrong. This will be actually 2ab, and a means ac by lambda minus ac by lambda dash. So it will be 2 into hc by lambda minus hc by lambda dash into m0c square to ab. So this term will also appear here. Okay, and this is nothing but 2 into hc upon lambda minus hc upon lambda dash into m0c square. Now it will be correct. Okay, so what we will have, so what we will have, we have just 2hc, if we take common 2hc into m0c square into 1 upon lambda minus 1 upon lambda dash. Now you can see this hc, h square c square, so this c square will be cancelled out, hc here also, so hc, so one h will be cancelled out, and c square will also be cancelled out, this c square will also be cancelled out, and this 2 will also be cancelled out. So it will be h upon lambda lambda dash into 1 minus cos phi equal to, there will be m0 c into lambda dash minus lambda divided by lambda lambda dash. So this lambda lambda dash and lambda lambda dash will be cancelled out. So lambda minus lambda dash will be h upon m0 c into 1 minus cos phi. So this is the result what we need. So this lambda dash minus lambda is nothing but delta lambda. This is the Compton shift. So this is h upon m0 c into 1 minus cos phi into 1 minus cos phi. So this is the more popular result of Compton wavelength shift. Okay, where m0 is the rest mass of electron, h is Planck constant, c is velocity of speed of light in free space, and phi is the scattering angle. Okay, so this is delta lambda. Okay, and this h upon m0 c is popularly known as Compton wavelength, that is lambda c. So you can write this equation in this way also. So delta lambda will be lambda c into 1 minus cos phi. So what is lambda c? So where lambda c is equal to basically h upon m0 c, and this is Compton wavelength. This is popularly known as Compton wavelength. Compton wavelength, and the value of this is, remember this will be very helpful, 0.02426 angstrom. Okay, so you can remember this result. Okay, now you can see if phi is equal to 0, okay, if phi is equal to 0, then you can see this delta lambda is 0. So if phi is equal to 0, you can see so delta lambda will be 0. So no Compton shift will occur. Okay, so then this is no shift, no wavelength shift, no wavelength shift. Okay, and this is too much significant, and this will happen only when the mass of the, so when the binding energy of the electron is so high. So why this is happening, you can see why this is happening. We have h of delta lambda is what we have. We have delta lambda is nothing but h upon m0 c into 1 minus cos phi into 1 minus cos phi. Okay, now you can see if the electron is not scattered, so that means the binding energy of electron is too high. You can see the binding energy of, you cannot tell electron is a free electron. If the binding energy of electron is too high, then you cannot say this electron is free electron. Okay, so in that case, what you have to take? You have to take the collision of photon, this collision of photon with whole atom, with the atom. So instead of electron, you have to consider in that case atom, because if the binding energy of electron is so high, then it will not recoil. Okay, so it will not recoil with too much speed or with too much kinetic energy, so that we can neglect the binding energy. So if the binding energy is high, so instead of electron, the whole atom try to recoil. So we have to take the collision between this photon and the whole atom. So in that case, you have to substitute the mass of atom here instead of mass of electron. So in that case, that will be that will be delta lambda will be nothing but h upon mc into 1 minus cos pi, where m is the mass of atom. M is the mass of atom, atomic mass. This is the atomic mass. Now this atomic mass is too high with respect to electron, because electron mass is very negligible. So if atomic mass is too high, then this delta lambda will be too small to measure. So you cannot, so that will not measurable. So in that case, you will get this delta lambda is 0. Okay, so if the binding energy of electron is too high, then you will always get no wavelength shift. But if you have phi is equal to, if you have phi is equal to pi, then you can see the delta lambda will be maximum. It will be lambda c into 1 minus 1, this 2, there are 2 lambdas. So that is nothing but 2h upon m naught c. So this is maximum shift. This is maximum shift. So we can draw a graph between delta lambda and phi. And draw a graph between this delta lambda and phi. The delta lambda, this is phi, graph will be something like this, maximum. So this is phi is equal to 0, and here this is phi is equal to pi by 2. This is lambda c. For phi is equal to pi by 2, you can see delta lambda is equal to lambda c, because cos 90 is 0. So this is lambda c. Okay, and here this is pi. Okay, so this is very important. This graph is very important. Okay, so you have to know all this thing that I have discussed here. In the next class, I will discuss further more about Compton effect, that is the kinetic energy of recoil electron, and the relation between kinetic energy of recoil electron and the photon. Okay, and the relation between this scattering angle and the recoil angle we'll discuss later in the next class. Okay, thank you.